NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, ladies and gentlemen. How is everyone tonight? Yeah, cool. Well, thank you, of course, as always, for coming out to join us tonight. Nearly 5 years after its amazing arrival at Mars, the Curiosity rover continues to reveal Mars as a once-habitable planet, showing that early in the planet's history, generations of streams and lakes created landforms that Curiosity explores today. Currently, the rover is climbing through the foothills of Mount Sharp, a 3-mile-high mountain formed from sediment brought in by water and wind. Tonight, we have two guests who will talk about the challenges of exploration with an aging robot, the latest findings from the mission, and what lies ahead. Our first guest is Mr. Jim Erickson, who started working at JPL in 1974 as a summer hire, and since there was always something fun to do, never left. During his career at JPL, he has worked on numerous spaceflight projects, including the Viking mission to Mars, the Voyager mission to the outer planets, Mars Observer, and he managed the Galileo project to the planet Jupiter. He then managed the Mars Exploration Rovers, the Mars Reconnaissance Orbiter, the Deep Space Network's Mission Support and Planning Program Office, and now the Mars Science Laboratory Curiosity rover. He received his Bachelor of Science degree from Harvey Mudd College in 1975 and his MBA from West Coast University in 1981. Tonight's second speaker is Dr. Ashwin Vasavada, who is currently the project scientist on the Mars Science Laboratory mission. He began working on the mission 13 years ago, and 2 years ago took over as the lead scientist. He has participated as a scientific investigator on the Lunar Reconnaissance Orbiter, as well as the Cassini and Galileo missions to the giant planets, specializing in understanding the environment of planetary surfaces and atmospheres. He has a PhD in planetary science from Caltech and a Bachelor of Science degrees in Earth and Space Science from UCLA. First up tonight, please help me welcome Mr. Jim Erickson.
Let me add a welcome from the project as well for everybody who came out to see this. I'm sure you're going to be very happy to see what we're all going to say, and let's get started. So, next slide. Whoop. First mistake. August 5th, or August 6th, depending on what time zone you were in at the time. We landed, we confirmed that we were down safely, and immediately got pictures back, including a really nice image of the target of Mount Sharp in the background. And then, of course, it was obviously time to see where Curiosity is going to take us. Now, this is where we've been. This is the route from landing up at the top of the star through our first stop at Yellowknife Bay, and Ashwin will talk about the rest. But there were some obstacles that we had to overcome. You notice the Bagnall Dunes, which are the dark area with very dangerous sand for a rover, and the fact that we found out we had a lot of damage being done to our wheels as we moved across the terrain. We figured out how to deal with that. Couldn't get rid of it, but we figured out how to deal with it and keep the mission going. And we continued, and we continued, and we continued. And in fact, we're the fastest thing on Mars. We were able to drive 17 kilometers in only 1,793 days, which is a record for any vehicle on Mars. It's kind of a small club, though, so yeah, you have to understand. And we weren't just driving. This is our vehicle, and it has instruments galore. Ashwin will give you an idea of what they do. We can actually do a lot of fun things. We can drill, we can scoop, we can deliver that kind of material to a couple of analytical laboratories inside the body of the vehicle. We've got a laser that can actually vaporize rock and look at the spark that you see there and determine what's in the material. So it's a really cool device, and it is extremely productive. And in fact, we are the most productive vehicle on Mars. We've got over 19.6 terabytes that are delivered to the archive and available for the public and scientists to look at. And to put that in context, I did a little Googling on the internet and found out what the size of the iTunes music store was. And we are almost 20%, 19 point a bunch. So that gives you some idea of exactly how much data that we've actually delivered. Now, I'm not going to belabor the point. Let's start looking at the data. And for that, Dr. Vasavada.
Hi, everybody. I'm really excited to tell you all about the last 5 years. We have, of course, a really productive rover, a really amazing robot, probably the most sophisticated robot NASA's ever created. And we had the honor of seeing it launch off to Mars 5 years ago, and actually planning it for about 8 years before that, and then arrive 5 years ago, and now celebrating this great milestone. So there's actually about, 6 to 10 hours of stuff I could tell you in the concise form of everything the rover has done. So I'm really condensing it down to really what has been the main story of why Curiosity was sent to Mars by NASA and the scientific community, and then everything that we've discovered that has informed that story. So the story of Curiosity really is about what we call habitability. Whether Mars ever offered the conditions that could support life. That's why Curiosity was sent to Mars. That's the place and that's the sort of role it performs in the larger Mars exploration program, from figuring out if Mars ever had water, all the way to figuring out if Mars ever had living things today or in the past. We're in the middle there, figuring out, now Curiosity was launched knowing that there's water on Mars, and we don't know there's life. So Curiosity has been asking the question, did Mars ever offer a full range of habitable conditions, not just the water, but the other things that life requires? And we have done a lot of work in that respect, and I am trying to make the case to you tonight of everything we've accomplished and how much we've learned of just how habitable a planet Mars is. So it starts all the way back when, the scientific story at least, starts all the way back when orbiters were orbiting Mars and mapping the planet in preparation for sending landed missions like Curiosity, and discovered a crater, Gale Crater, that had a weird mountain in the middle of it. And so this is just a nice illustration of Mars with an orbiter there, Mars Reconnaissance Orbiter, which is one of the current orbiters at Mars. Gale Crater has been actually mapped by 3 different missions, and one of the things that really made Gale Crater stand out was this mountain in the middle of it. Craters, for example, on the moon of this size, about 100 miles across, would not have a large mound like that. They just have maybe a central peak, a very sharp mountain. And that exposed a difference, of course, between the moon and Mars, that the moon has no atmosphere, but Mars, having an atmosphere and even maybe water in the past, can move stuff around, can erode rock from one place and move dirt around and collect it somewhere else. That was a huge discovery for the promise of doing geology on Mars, because layered rock lends you a record, leaves a record behind that you can explore on the ground with a virtual geologist in the form of a rover. So here's Gale Crater, 100 miles across and about 3 miles deep, and there's the central peak that probably formed with the impact. But all this stuff, this is 5 kilometers, 3 miles high of layered rock that we can see from orbit, discovered by the Mars Global Surveyor, one of the initial orbiters in the Mars exploration program, to consist of layered rock that we think was brought in by water or wind in the past, and leaving this a very important record for us today. The other things that the later orbiters found, including the Mars Reconnaissance Orbiter, which continues to be our communications link back to Earth every day, that orbiter has a scientific instrument that also found that these layers change with height. As you go from the bottom of the mountain to the top, the minerals that are in the rock change, the chemistry, the texture, the look of the layers change, which also was just very exciting news for the idea of being able to land a rover here on the plains where it's nice and safe and drive over and then slowly ascend through these layers and read Mars's history, like a book, page by page, every layer being laid down on top of the next as time advanced in early Mars history. So that's kind of sets the context for why we chose this particular landing site. Now I'll just kind of zoom in a little bit and show you where we are today. Yeah, here's Gale Crater again, a really gorgeous picture showing the mound here again, the central peak, the 100-mile crater. A lot of dark sand that's collected. This is probably modern sand that's blowing around today. And you see this little strip of dark sand. Those are those dunes that Jim mentioned. And here's where we chose to do our field area. This is where we sent the rover. This is where we plan to explore. And that map that Jim showed all fits in this little box right here. So here's that dark strip of dunes that goes across. We landed out here on the plains there, drove across the plains, started climbing the mountain. This took about 2 years to get to this point after spending a lot of time at Yellowknife Bay, where we made some of our most important initial discoveries. Reached the mountain here and have spent about 2 years climbing to where we are today at this star. We're just about to ascend what's called the Reuben Ridge, a big ridge that forms one of these major layers on the mountain. And then we'll get to a clay unit and a sulfate unit. But most of the past 2 or 3 years we've spent on the mountain itself has been in this initial layer of the mountain called the Murray Formation. It doesn't have a fancy name like clay and sulfate or hematite because we didn't know what it was made out of when we landed there. So we just named it after Bruce Murray, one of the founding planetary scientists at Caltech. And so we've been spending all of our time here so far, and we're about to get to the next layer. But now, keep your eye on that map. We're now just about to ascend the ridge, and this box here is this image from the Mars Reconnaissance Orbiter. Yeah, and there, look at that. That's Curiosity right there. 6 feet across, and you're looking down on Mars from 200 miles above the surface. So this is like looking at a car on the freeway in San Diego from Los Angeles. We love the Mars Reconnaissance Orbiter not only for telling us about Gale before we landed, but for sending our data back every day. But it also continues to watch over us and make sure we're still there. So I couldn't resist throwing a couple of pictures of what we've been doing lately, and then I'm going to launch into that big story about Mars habitability and climate. So here's some sand dunes. This is when we were actually crossing those big sand dunes that Jim mentioned we saw on that map. What I love about this is not only because it's a selfie, which our camera team learned how to take. They realized that a camera on the end of your arm isn't good just for looking at the microscopic details of the rocks and soils like it was designed to do. You can also raise it up and look at yourself. Thank all the millennials for that tip. But it actually takes about 55 images and 55 positions of our arm, because the camera isn't designed to be a selfie camera. It's designed to be very narrow angle. So this was a lot of work, actually, by all the people who did this, but you get these spectacular pictures. And then you Photoshop out the arm, and it goes away. But what's amazing about this dune, to me, one of the things that I just keep coming back to with this mission, and Mars, in fact, is just how Earth-like the planet is. Especially when you bring really good cameras to Mars like this, you have to keep telling yourself, like, this wasn't taken in the desert, out of Barstow or somewhere. And one of the ways I can try to prove that to you, actually, it's not a conspiracy, is that this dune, what I love about it is it's so Earth-like in one sense. The wind is blowing just like it is on Earth. The wind is picking up debris in the sand and making that move around just like sand does on Earth. And sand piles up in dunes just like on Earth. And ripples form on the sand just like on Earth. But one thing you will never be able to see on Earth that's in this picture are these wavy ripples. They only form, that wavelength of ripple and that shape only forms in the thin atmosphere of Mars. So no Earth dune has these little S-shaped ripples that are about 3 feet apart. And that is because Mars has this 1% thick atmosphere and different physics applies. Still similar physics enough to form dunes, but different enough to form different ripples. So on this picture, you kind of see Earth and Mars, which I really love. The Reuben Ridge, we're about to ascend. This is an 8-story wall of rock that we knew we had to cross to get higher up on the mountain. And we're currently driving along the base of it, taking all these wonderful pictures, and then looking for the place where we can climb up. We actually, it's not too risky because Another thing that the Mars Reconnaissance Orbiter and other orbiters allow us to do is actually map the planet before we get there and make sure there is a route we can climb up. So we have a good idea that there's a place that's just not too steep, so we can make it up this 8-story wall of rock and continue on up the mountain. But we're not there yet, so we're on the wall part right now, not the less steep part, and seeing what this ridge is made out of. And again, the questions we're asking start with geology in most cases. Why is the ridge there? It's been flat for so long, and why all of a sudden is there an 8-story wall of rock? So something about the chemistry that may have changed. This ridge is called the Reuben Ridge after a pioneering astronomer that inspired a lot of our team members, but it's actually also called the hematite unit or the hematite ridge because the ridge has this mineral hematite, an iron oxide. Iron that has that's combined with oxygen, been oxygenated or oxidized, and forms this mineral, this reddish mineral hematite. So that's a clue. So maybe there's some process that brought iron in from somewhere else. The iron was dissolved in water and hit the atmosphere at this location of the ridge and got oxidized by oxygen in the atmosphere. That's maybe a theory. There's a lot of other ways this could have happened. We're trying to figure out why the ridge is there, why the hematite's concentrated there, and of course, what that means for the habitability of ancient Mars. Here's another gorgeous view of the hematite ridge just from a couple weeks ago, and Mount Sharp in the background. And we're now seeing that this ridge itself is composed of extremely fine layers, and it was once buried, and when it was buried, it broke into all these chunks, and then groundwater, as it was buried, flowed through those fractures and precipitated these whitish minerals, which are almost like hard water deposits. They're dissolved minerals in the water that then fill up the cracks. And so this ridge just has a lot to explore, and that's what we'll be doing the next 3 or 4 months. But let's get to the main event. That's sort of where we've been doing. I didn't want to start with like a bunch of slides that didn't include some nice pictures at first. So now we're going to launch into a story about the climate and habitability of Mars that'll last the rest of the talk. So here's Earth and Mars. We love how beautiful our planet is, but Mars is not too bad itself. It's about the relative size compared to Earth, much farther away, of course, than shown here. It has polar caps, so sometimes it's portrayed like, does Mars have water? We've known it's had ice for decades, since the 1970s, 60s even. So Mars has a ton of water, it's just all frozen now. And the atmosphere is very thin, so it's actually too thin to have liquid water. It would all actually boil or freeze almost at the same time in the very thin atmosphere of Mars. But it does have clouds, these little wispy water ice clouds. And so today, Mars isn't really a very appealing place for life. We've sort of accepted that, even though we'd love to find if there's any life on Mars. And today, unfortunately, also extends back about 3 billion years. We think Mars had the same dry and cold conditions. It's a little further out from the sun than Earth, so it's quite cold for probably the last 2 or 3 billion years. But maybe Mars, we think, actually, was quite different early in its history from the time it formed, maybe after it initially cooled off, until maybe 1 billion years after it formed. And we have evidence to cause us to think it was quite different. So keep your eye on Mars right now. This is pretty cool. Maybe it was like that. So this is probably the best case scenario. I'll admit that. As a scientist, I have to be honest with you. This is like Mars with a giant northern ocean and a huge water cycle with hurricanes. This is probably the ultimate early Mars. It may have also been some less exciting version of this, but still very different, where there was rivers and there's lakes, and that's what I'll show you we found, in fact, at Gale Crater. Here's some of that evidence for why we are, long before Curiosity got there, we think that Mars did, in fact, have a lot more water in the distant past. This is one of the early pictures of Mars from probably the 1970s, where in the 60s, let me start there, JPL, just a few years, like a half a decade after Sputnik, JPL already had a mission flying by Mars taking the first pictures. And at that point, in 1965, I think it was, Mariner 4, there was, you're coming off of hundreds of years of history where there's sort of just ignorance about Mars, so there was thought that there still could be life on Mars, intelligent life, plants, whatever. 1965, all that excitement with a spacecraft flying by, and the first pictures were fuzzy pictures that just had craters, and it really took a lot of it disappointed a lot of people, from what I hear. I wasn't even born yet, but but it had a lot of craters that looked like the moon. So, oh my gosh, Mars is totally dead. But then just a few years later, pictures like this started coming back from the follow-up missions. And these are craters that made people think that maybe it was like the moon. But look, in between the craters on the plains, there's river systems. This is hard to get around. That water flowed around the surface, and flowed downhill, and streams joined each other just like they do on Earth and made bigger rivers, and they flowed for sometimes hundreds of miles across the surface of Mars. A little later in the history, somewhat younger features get even more dramatic. So these are actually channels, catastrophic flood channels. So these channels here are maybe several hundred feet across, a quarter mile, third of a mile wide. These channels can be 50 miles wide, 100 miles wide, giant swaths of Mars where just huge amounts of water flowed across the surface, probably in catastrophic flows, not over and over again, but just a huge flood. But there's a lot of these. And so something dramatic happened at that point in Mars history. And then we started seeing pictures like this when we sent even more sophisticated orbiters. And this was discovered by the Mars Global Surveyor in about the year 2000, I think, where at the end of some of these river networks, we call them valley networks, they empty into craters like this. And where they empty, they spread out into a fan. The sediment that's left behind spreads out into a fan. And people, found these, and after studying them and trying to disprove their hypotheses about these, they're left with the idea that these are deltas. So a river flowed into a crater, brought in a lot of silty, muddy water, met a standing body of water. That's the way you form a delta, like the Mississippi going into the Gulf. And the sediment the water causes the river to suddenly slow down, and sediment drops out, and it kind of spreads out, and you form this big mound that's a delta with all these different branches that the river takes as it enters the standing body of water. So this was evidence that not only were there rivers, but they lasted a long time to build up a giant feature like this, and there were standing bodies of water in these craters. So here's sort of the history of the climate of Mars. How did we get from here to here? We started 4.5 billion years ago, and that geological era, because of all these great features that look like they were caused by water, we call that the Noachian, like Noah. And that's where the valley networks are. So this is like, Jurassic Park, those ages on Earth. We have ages on Mars too. Not the Jurassic, but the Noachian, Hesperian, and Amazonian. And the Noachian is where you see the valley networks, all those rivers. The Amazonian is the 3 billion years to the present, where it's just wind and ice really formed everything, not much liquid water anymore. And then the Hesperian is kind of this mysterious time in Mars history where there's not as much evidence for long-lived rivers, but it's not quite dry yet, and you have these catastrophic floods that, what's the deal with those? And so this is actually a quite interesting time to explore. And in terms of climate, when you ask yourself, what was necessary for the climate system of Mars to be able to form those features and to have a hydrologic cycle, for example, that could supply rivers and lakes, we've concluded pretty much as a scientific community that Mars was wet. Hopefully you're convinced of that. It's hard to deny all that real geologic evidence. And maybe even warm. You could have had ice that occasionally melted and formed these rivers and lakes, but a much easier way to do that is you find some way to heat up Mars with a thicker atmosphere maybe, and then it's warm enough to actually have a hydrologic cycle with a humid atmosphere and evaporation from one place and rain in another place, and then you really get a very Earth-like early Mars. There's problems with this, actually, which make it all the more fun to think about. And the same problem actually is true for Earth, in fact. When you look at stars across the universe, you kind of come up with a life cycle of stars, and they start glowing less brightly and as they get a little older and they get into their, I don't know, their teenage years. They get very strong and bright. And there's a thing called the faint young sun paradox, where you have a lot of water on Earth when the sun shouldn't have been bright enough to allow it to be liquid. And the Mars is even worse. The problem is even worse at Mars, where the same faint young sun existed 4 billion years ago. Only about 75% of the energy that comes off the sun today was present in early Mars. And we, frankly, don't have any climate models that take that sun and predict a warm and wet Mars. So this makes it really fun for us on the Curiosity mission to find a lot of evidence, which I'll show you, that says it was probably warm and wet, and yet the people who run climate models have no idea how to make that work. So see if you believe it. So what's cool about it is that Gale Crater is right in the Hesperian. So the crater didn't even form till about 3.8 billion years ago. So we know that everything Curiosity's seeing is from the Hesperian onward. And we think that entire mountain formed and lasted a few 100 billion years. And so, 100 billion, geez, 100 million years. So from 3.8 to maybe 3.2 billion years ago is all the stuff you'll see in our pictures, other than the sand that's blowing around today. But all the rock, all the mountain parts are formed in this time period. So we get to explore this really interesting time and ask, was, right here at the beginning, was Mars wet and warm? We can sort of infer what might have been the conditions here, and then we can ask, how long did those conditions last? And what does it mean for the possibility of life? I think that was my next slide. So this is sort of where we are with the Curiosity mission when we started. Mars was once wet, and we want to know, was it also warm? And the specific question, of course, that NASA charged us to answer is, was it habitable? And if there was ice and it melted for a day, that's not really that interesting for life and habitability, because life can't evolve in 24 hours. So, but if we can find that these wet conditions lasted for millions of years, tens of millions of years, hopefully longer, that gives life a real chance to do what it did on Earth. So habitability. This is not Mars. This is one of the, for us, less habitable places, if you like spending time in Death Valley, but perfectly habitable. And so you have, when I give talks and there's 8-year-olds, I make them answer, what is habitability? What conditions are required? But I will make you answer. So liquid water is the first one. When we think of what are the essential characteristics of an environment that life can exist in, liquid water is always the top of the list. Every life form we know on Earth requires liquid water, and it actually requires not only liquid water, but liquid water that's the kind of the right liquid water, not too acidic, not too much dissolved in it. If it's too salty, things don't live. That sort of thing. So we need to be a little more sophisticated than just finding evidence for liquid water. We need to ask, what's the water like? The key chemical ingredients for life, at least by analogy with Earth. We're not talking about science fiction here. Our best way of looking for life on Mars is by analogy with us on Earth. And living things on Earth share a lot of common characteristics in terms of the chemistry. So carbon, hydrogen, oxygen, sulfur, phosphorus, nitrogen. There's 5 or 6 elements, plus a few others, that are common denominators for all of us and bacteria and everything else. So let's see if Mars had those to provide as raw material for life. And then energy for metabolism. We all need sources of energy. We eat things, who eat other things, and eventually use the sun or something like that. There's a food chain we're on the top of. On Mars, probably no food chain. Probably if life ever existed, it was probably just really basic life. And so it could use sunlight. But one of the interesting things that we can look for on Mars also is the way that certain microbes on Earth can use chemistry for energy. So you can dig down, or you can somehow get a mile below the surface of Earth and find living microbes. And some of them are actually able to use the chemical differences between rocks at that depth. There are minerals in the rocks, and create little batteries that between different chemicals, and allow them to source that energy to live. So we can look for those similar types of sources of energy on Mars if life may have been underground. And then how do we look for all this? How do we study habitability? Jim did a great job of describing the rover. We love the laser. It's the most fun experiment to run. But the way we really, the way that we get at the habitability issues and the chemical ingredients necessary for life and the raw material and all those things in the most in-depth way is through our drill, which we place against a rock and drill powder and deliver it to 2 laboratories that are built in the front of the rover. So this was a real feat for the people who designed and built the rover to actually fit in laboratories. These are laboratories that would fill a better part of a university office, in a geology department in a university. This is a mass spectrometer and a gas chromatograph and a tunable laser spectrometer. Probably spread it out over like a huge room in a university, but you shrink it down, you miniaturize it, you stuff it all in a canister about the size of an old microwave oven, and you gold plate it because it's cool. And then, and then you carefully put it in the rover. And so this is one of our main laboratories called SAM, Sample Analysis at Mars. Everything's an acronym. And 650 yards of wiring, ovens that heat up the rocket soil to 1,000 degrees and decompose it, degrade it so that the gases come off and we can study them. And some of our most nerve-wracking mechanisms on the rover, 100,000 RPM vacuum pumps, which you can never maintain. You send them to Mars and you hope they keep working. This is the kind of thing people would, we get nervous about sending any motors to Mars, even simple motors, but 100,000 RPM pumps, they're still working. So here, we landed. So 5 years ago, at actually 10:30 tonight is when we all gathered here at JPL with about, I think, 1,000 other people to listen helplessly, actually, as Mars Curiosity sent back signals 14 minutes old as it descended to the surface. I'd show you the movie. It's super fun, but go watch it online if you want to relive it. These are the scour marks from the rocket engines that were on a little jetpack that lowered the rover to the surface. And they actually led to one of our first major discoveries about climate and habitability. This is Mount Sharp. Those are those dunes. So, we landed quite far away, and since then have traversed across those dunes and climbed a little ways up the mountain. But here are those scour marks. And we looked up close just, days after landing, about a month after landing, we got to this site where we found these, what looked like upturned pieces of sidewalk. And it turned out that they were a rock called a conglomerate. That's a rock made out of a bunch of other rock that's cemented together, just like a sidewalk, actually. As the rock was falling apart after a few billion years of sitting there, the pebbles that were coming out were all distinctly rounded. You can see that, and that is something that doesn't happen too easily, in the natural world. When rocks break, they are very sharp and jagged. But if they're, rolling around in a stream, for example, for 10 miles or so, you can round them like is seen here. And so we already had this really, visceral evidence that we were traversing across an ancient stream bed just a month after landing. And we thought that might be the case from outlines of an ancient river that we could see near our landing site. But this is really the first time that we've been on the surface of Mars and with our own, robotic eyes, seen something that we can all relate to, rounded pebbles in the bottom of a stream bed. We then drove over to Yellowknife Bay, and so here's Mount Sharp. This is one of our gorgeous images from our navigation cameras, which are grayscale black and white cameras. This is our arm deployed at the surface. We're about to drill here. And you'll notice how dramatic the scenery has changed. But in the image you saw before, there's a bunch of gravel, little rocks everywhere. Now we're in these big slabs of rock. And what attracted us to this site is, again, from looking at the orbital pictures, thinking that stream might have led to an ancient lake at one point. And when we got here at the site of this, what we thought might have been an ancient lake, the rocks all of a sudden turn into these big slabs of very fine-grained material. And so far, that was really good news for the fact that it could actually be lake deposits. And so, of course, we wanted to drill it. I love these pictures of our drill holes. The drill hole is only a dime size, so to kind of give you a sense of the scale. And we have, this is one of my favorite pictures of the whole mission, just because how cool it is. But we drilled this hole, and we took a picture of it from about 7 feet off the ground, looking at a dime-sized drill hole, so we have great cameras. And then we shot it with the laser, again, from 7 feet off the ground into a dime-sized drill hole, to see if the composition changed with the drill, with the depth of the drill. And then we saw this gorgeous mineral vein, which is, again, that sort of hard water deposit stuff, calcium sulfate, which probably was groundwater flowing through the rock after it hardened. This is also really one of my favorite pictures. You get to see like my favorite pictures of Mars tonight in the 5-year anniversary talk. What I love about this one is that we took it with our own lights in the middle of the night. And so all the other pictures of Mars you'll see are sort of falsely, or as best as we can do, corrected to remove the orange glow of all the dust in Mars' atmosphere. So if you just snap a picture on Mars, it's very orange. But we try to color correct them so that human eyes can sort of better understand what's going on with all the orange. But this one is a real picture because the glow of the orange sky is gone at night. And when you bring a LED, a little your own flash, with you on the camera, you get this is the real color of Mars. And so what was cool is that we drilled into the rock, and the material inside the rock wasn't red, which is true of most of the oxidized parts of Mars. It was actually gray, and so that was great evidence that this material hadn't been exposed to a lot of harsh conditions like other parts of Mars that have been oxidized and weathered, and may actually, preserve evidence of the conditions from a long time ago. So again, fine-grained material, and then we analyzed it in our laboratories. And we found an ancient lake based on the geology. We found fresh water based on the minerals that were in that drill hole. We found clay minerals in particular, phyllosilicates, that form when water interacts with rock, but not just any water, water that's not too acidic. We found not too many salts dissolved in that rock, so the water was basically fresh water available for life. And we found key chemical ingredients of life. We found carbon and nitrogen and oxygen and sulfur and phosphorus and nitrogen in the form of nitrates. That's actually a nutrient for life, a form of nitrogen that life can use. And we found organic molecules. We found simple organic molecules, not like DNA quite yet, but we found organic molecules that at least showed that Mars had already begun to naturally probably assemble larger molecules out of carbon and hydrogen and oxygen. And those molecules, very importantly, survived 3 billion years sitting in these rocks. So in future missions, when we go look for life or return samples back from Earth, this is one of our main findings from the mission, is that we have hope that even old rocks have preserved that evidence that we can bring back and study on Earth. Okay, so I got to keep this from going into the 3-hour version of the talk. So I'm going to speed up. But this is a little map of Mars, of the mission really, in sort of profile. We landed out here in Yellowknife Bay. We drove across the plains. And that's sort of where we spent the first 2 years. So I got just a couple pictures of what we found there. Another one of my favorite pictures. This is, we came across this amazing landscape where the fine-grained, muddy mudstone, we call it, the lake bed deposits, had gone away, and the gravel had gone away, and there was this amazing set of these linear beds of sandstone. So now not mud, but bigger particles of sand that had formed slabs, and you can see all the slabs are kind of tilted away from you towards Mount Sharp. And this was, again, studied. We tried to come up with a lot of ways of explaining this, and as good scientists tried to prove ourselves wrong in each case. And the theory, the hypothesis that survived was that this was a river delta. And so we now had seen a river bed, a stream bed. We had seen the lake bed of a lake. in Yellowknife Bay. And then now we find the interface between those two. Where a river meets a lake, it forms a delta. And it forms the delta out of sand. That's the particular size of particles that first gets dumped out of the water when a flowing river hits a lake. This made kind of an amazing prediction, though. It suggested that there was a giant lake that probably filled in much of the area in this picture. And in fact, what's not obvious from this picture, but everything sort of goes higher and higher. So there's a lake, a delta here, and then all this rock above it. So that doesn't quite work. How do you have a lake in front of you when the mountain is climbing up in front of you? Unless the mountain wasn't there when the lakes were there, and instead the mountain itself is some remnant of lake beds that were built successively over time. So that was sort of a crazy hypothesis, but we had to go test it, of course. As we got to the mountain, the prediction was we would find lake bed sediments like at Yellowknife Bay, but in the mountain itself. And that's what we found. Remarkably, we got to the base of the mountain, and we found these very thin, repetitive layers, 2 millimeters, 3 millimeters thick, hundreds and hundreds and hundreds of them. You can form those by wind, for example, blowing around sand or blowing around dust. But when you do that, you tend to form more wavy beds that you follow one layer and it kind of ends, and then another one starts. It's called cross-bedding. You can follow these layers for a long ways across the entire surface, and it's very consistent with very slow sedimentation inside a standing body of water where it's calm water, the lake floor just goes on forever, and you just deposit a very thin layer year after year, decade after decade, and you build up years and years and decades and eons of time in these deposits. So we found this at the base of the mountain, and then of course we wanted to figure out how much of the mountain, how long does this story go on? How long did the lakes last? So that's what we did. We got to the mountain here, and then we were in the Murray Formation, this main first layer of the mountain that we've been in for the entire time up until about a month from now, when we actually climbed the hematite unit. And we first had to drive across some obstacles. One of them was called the Stimson Formation, which is another geologic term we use for a bunch of sandstone that probably came in, we think, later. And it just is sort of a younger thing we have to sort of drive around to continue to find more lake bed deposits. Here's what it looked like as we were driving across towards the higher parts of the mountain. This is one of my favorite pictures. And the reason it is, in this case, is because it shows such great variety of all the materials that we studied. There's the gravel. There are these dark rocks that is one of the more mysterious things. We don't really understand these very dark rocks. They're kind of rare, but here there's a bunch of them. There's the sand that we've studied many times. There's the mudstone, the lake bed deposits that look like this. There's sandstone that came later, the Stimson Formation, that forms these mesas and buttes. And then there's the rounded domes here of the sulfate unit that's higher up on the mountain that we maybe get to in a year or two. And then the upper parts of Mount Sharp. And here's what it looks like when we're at the interface between the mud of the lakes and the sand of the Stimson Formation. And we got a really good look at the Stimson here, which is the sandstone that came later. And actually, this is the site where we pieced together the history of did it actually come later. And we did that at what's called a geological contact, kind of a word that probably makes immediate sense to you, where two things touch, the contact. And that's one thing where you can learn about how one episode of forming rocks turned into another by looking at their interface. So we spent a lot of time in this area called Mariahs Pass studying the details of this interface and figuring out that the mudstone formed, eroded away, then sand blew in by the wind. This wasn't formed in water at all. And sand dunes built up. And then those dunes turned into rock and left these amazing sandstone formations behind. And if you think those are pretty, look at these. These are just amazing landscape, like you're in Utah or Arizona or somewhere. These are the Murray Buttes, and here's all the lake bed mudstone that we continue to see over and over again as we climb the mountain. And then the later sandstone came in. You can imagine that all these were once connected. There was a whole thick layer of sand that blew in and then was buried and turned into rock. And now most of it, 90% of it has been eroded away and blown away, and you just leave these impressive towers behind. And the tower is sort of protected by this capping rock that protects it from erosion, and slowly blocks fall off. And if you come, 10,000 years from now, it'll be a little smaller, and a million years from now, it might be gone. So then we really got to the good stuff when we passed through the Stimson Formation, and we got to where the mountain just starts taking off in elevation. And so we've been climbing now for the past few years through the bulk of the Murray Formation, almost 600 feet. And this offered the opportunity for us to kind of change our approach. The variety sort of went away. There was not the buttes anymore and the sandstone. It was just all mudstone. And so we came up with a process of every once in a while just drilling regularly. Every 25 meters, we said we're going to drill a hole and build up a record of how the Murray Formation changed over time. Because if it was all lakes, maybe the lakes changed over time. Maybe they came and went. Maybe their chemistry changed and their habitability conditions changed. So let's just build up a record. And that's what this shows. We've now drilled 15 times on Mars, and we've scooped up sand and analyzed in our laboratories 4 times. And these are all the drill holes that we drilled in the Murray Formation. And you can see there's a lot of variety. Even to your eye, some of it is the less weathered, oxidized material that's grayer. Others, it's distinctly red, like most of Mars appears, because it's more oxidized. And so by drilling successively as we climbed through the Murray every 25 meters, we could see that the environmental conditions were actually changing. And we, of course, wanted to understand what that meant for the prospects for life and habitability. So, I won't go through all this, but this is sort of one of the ways that we visualize the data as a science team. These pie charts represent the different minerals that are in the rocks. And so out here on Yellowknife Bay, there's a lot of green. Those are the clay minerals, the ones that really are the definitive evidence for water interacting with rock in a lake, and fresh water and less acidic water. Then we got to the base of Mount Sharp, and we still had clays. We still had the lake bed deposits. But we started seeing a bunch of this red pie slice, which is hematite, which is this iron oxide. And so the conditions that were very unoxidized, not too harshly weathering back at Yellowknife Bay seemed to have gotten a little harsher, so to speak, more weathering, more oxidation, even though the clays were still there and the lake was still there. And as we got even higher, even the hematite went away, and even some of the basic rock-forming minerals went away. And this drill hole itself was just left with one of the basic parts of a rock, which is silica, and not too much else. And so what was beautiful about this is we had some patterns that we could try to explain, interpret by environmental conditions changing over time, because each one of these drill holes is higher than the next by 25 meters. And I'll focus on how we have 2 explanations. It's a nice, friendly competition in the science team. We have a lot of data, and we have 2 different models to explain it. And then as we got even higher, we saw this very different looking combination of minerals. And then we saw 3 drill holes that were almost identical to each other, and suggested that conditions actually weren't changing too much in that part of the mountain. So briefly, one idea that explains the clays and the hematite down here at the base of this 30-foot section of rock where we drilled 3 times. These are a little tighter spaced than 25 meters. We drilled 3 times in a row right here. Is that the lakes were there, they deposited sediment, and then groundwater later on flowed through these rocks, and it was slightly acidic. And it actually took it dissolved, with acid, some of the parts of the rock and minerals, and delivered them down to these areas. So we see more hematite, we see more trace metals down here, and we see a lot of these are just depleted of a lot of their initial minerals and chemicals. So that was one model. Another model that does a pretty good job also of explaining the same data, so it's fun to have these competing ideas, is that there was a lake, or a series of lakes really on Mars, that had different amounts of oxygen dissolved in it. I didn't know this on Earth, but maybe some of you are fisher people, and there's more oxygen near the shore of a lake, and when you get deeper water, there's less oxygen, and so a lot of stuff lives in the more oxygenated part of the upper surface of the lake where it mixes with the atmosphere. And the same thing would be expected on Mars if the lakes were kind of placid and not overturning too much. You'd get more oxygen in the near shore part of the lake, and deeper down, less oxygen, less oxidant, of either caused by ultraviolet light or oxygen directly mixing in from the atmosphere. And so you might find that if we drilled in a rock that was once part of a near-shore environment, you'd have more hematite, and you'd have more of those oxygen-enhanced minerals. And if you drill a hole that once was in the deep part of a lake, you might see that change to the other classes of minerals that we found in the other holes. So this does a pretty good job of explaining the mineralogy, the chemistry, and fits in the lake hypothesis too. So now it's just left to really gather more data and think through and really see which one of these ends up winning the day. So to finish up our exploration of the Murray, a couple more interesting things. This was a really cool find for us, a picture of mud cracks on ancient Mars. This is a slab of rock about 2 feet across, and it really was striking. We hadn't seen anything that looked like this when we came across it, where you have these little rectangular patterns all over this rock, just maybe an inch across each, and very angular patterns. And it really struck a lot of the geologists on our team immediately as desiccation cracks. Cracks that form like in a drying pond in the middle of summer on Earth. The water goes away, the mud's left behind, and you get these, we've probably all seen it, these little square blocks of mud. And this was what it would look like if the layer above this rock layer had all those cracks and sort of left their imprint, and because you see these as ridges. So it's almost like a plaster of Paris imprint of mud cracks. And they were confined to this thin red layer. We measured the angles and the geometries of all these cracks and compared them to mud cracks on Earth. And it turned out, again, that this was the best scientific explanation for this rock. And, all that's very academic. But then, I think about this, and it's just amazing, because to me, it's not a dinosaur. We'd love to find a dinosaur. But if you're a geologist, this is, getting close to finding like the dinosaur footprint, where we're looking at like, a day or a week on ancient Mars. You're looking at, there was a lake, and one day the lake dried up, and the mud cracked, and then we're looking at it 3 billion years later. It's just kind of like mind-blowing in a way. And so this was evidence now that the lakes didn't last forever. In fact, the higher we got on the mountain, we started seeing more things like this, where the lakes actually disappeared every now and then. So that's interesting. So we're beginning to see maybe a twist in the plot of the history of Mount Sharp and Gale Crater. And yet, after this, we've seen more of those continuous thin layers again. So the lakes came back. But we think now, for the past maybe third of the 600 feet of Mount Sharp we've explored, that the upper third is a lot more intermittent than the bottom 2/3. But if your hopes for ancient life are waning, I will cheer you up again, because after all those lakes went away, even the ones that came and went, all this stuff was buried and turned into rock and fractured. And the fractures are just everywhere we look. They're filled with this calcium sulfate. So that means even after the lakes dried up at the surface, there was still groundwater flowing through the ground and bringing chemicals from one place to another, dissolving calcium and sulfate from one place, filling cracks and leaving these little fins of calcium sulfate for us to find today. So the history of water in Gale Crater isn't just confined to the lakes, but also as long as the groundwater lasted after the environment at the surface may have been too dry. So in the future, we're going to keep climbing. We still got a lot to do. We are now at the hematite ridge, which is this wall. So we're actually down here now with the rover. We're going to ascend the wall and go over it, get into a big unit of clay that's still further up. So the amazing thing is all the clay we found so far wasn't visible from space. from the instruments on the Mars Reconnaissance Orbiter that can detect clays from space. We don't know why exactly that is, but we discovered them because we were there and were able to drill. But the clays here are a bright signal up to space that there's clays in these rocks. So we've been waiting to get to this clay area since before landing, since we picked this site. So that's going to be very exciting for us to get there and see what it means for another possible lake environment. So to wrap up here we are with the story of climate and habitability on Mars. Mars was once wet. Was it warm? I think it's quite likely. And the reason we think that is, in spite of the faint young sun paradox, is that the lakes were there for so long and they were so continuous that it's very hard to explain them by the other creative ideas that scientists have had of how you can get the rivers and floods in a permanently cold environment. You have to have like a volcano goes off and makes gases in the atmosphere that temporarily create a warm planet for 100 years or 1,000 years, or you have a meteorite hit and also create a temporary atmosphere, or you have seasonal ice that occasionally trickles out a little bit of water. None of those really can support the amount of water we see that would be required to build up all these layers, which are 30 miles of lake sediments that build up hundreds and hundreds of feet thick. So you have to have a lot of flowing water to deliver that sand, to deliver that sediment. And then if you just take kind of rough calculations of how long it would take to build up 600 feet of lake bed deposits based on analogy with Earth, it's probably millions to tens of millions of years. So that's not a lot of time in the billion-year sense, but it's a lot of time to explain unless you had a humid atmosphere that was stable, like a stable, warm, early climate of Mars. And so I think the legacy of the mission is going to, one of the legacies besides the main one, which of habitability, is going to be that we threw a wrench into our understanding of the climate of Mars by showing that in the Hesperian it remained warm and wet, and quite likely Mars had a pretty good hydrologic system. I just said that. And so what's next then? Curiosity's doing great. She's getting a little older. Things are starting to break a little bit, but we still got a lot ahead of us, and we think we still got, 3, 4, 5 years of great science ahead at the clay unit, the hematite ridge, the sulfates beyond, and we'll complete, the story of the climate in the Hesperian. We've based on the chemistry of all that water and the fact that we found organic molecules, we've also, it's synonymous to us with habitability. So not only did water last millions to tens of millions of years, but habitable conditions, more importantly, lasted that long. And that's the kind of time scale that life can really begin to make use of in terms of originating on Mars or being delivered somewhere else and evolving and surviving on Mars, spreading on Mars. So that, and combine that with our third contribution, I think, of this mission, which is finding organic molecules that have been preserved for 3 billion years, that really sets up this good-looking rover, because it's based on Curiosity. This is the Mars 2020 rover, which looks a lot like Curiosity, but will actually be sent to Mars to seek signs of life. And this was planned optimistically, hoping that Curiosity would find that Mars was once habitable and capable of preserving signs of life. And now that we have shown that that's possible, this mission is our best chance for actually determining if life ever took hold, both by the instruments it carries with it to Mars to explore an environment that we think is habitable, and by collecting samples that one day we might be able to return back to Earth and study in the best laboratories on Earth. So that's kind of where we are, and thank you very much. So with that, Jim and I would love to take questions for 10 minutes or so, and please use the microphones. and fire away.
You guys ready?
Sure.
So what'd you guys do with the wheels?
Okay, we did a lot of things. The first thing was to really test them to find out what was going on Mars. We spent a lot of money buying brand new wheels and destroying them with the kinds of things that we thought might actually be what's contributing to the damage, characterizing it, and then basically building models as to how we could drive in this kind of a terrain, how far we would be able to go, how much damage we would get if we ran on the really sharp, jagged stuff versus the sand. And then we sort of keep that in mind whenever we make decisions about what routes to take to avoid the worst stuff. But sometimes the good science is where the rough stuff is, so we make those kinds of trades. In addition, we actually built software that allows the rover to drive softer. Specifically, it's called traction control, and it basically says if one wheel is going over a rock, everybody else slows down so it doesn't get pushing that one wheel into the rock. And that looks like it's working quite well. And so that's another thing that's going to stretch out the life of the wheels. Right now, we have enough life in these wheels that we're going to be able to get to the top of where we want to investigate on Mount Sharp with margin. And that's a good thing, and we'll see what happens afterwards. And already people are starting to think about traction control Mark II and make it even better and softer.
I have two questions about the soil, and I understand there's quite a bit of radiation on Mars. And the first question is, do we know whether the soil would, or any of the soil you've analyzed, could support life like the astronaut in the Martian movie raising potatoes? And the second question is do we know whether we could make glass out of the soil to use as radiation shielding window?
The first question, I think one of the challenges is the soil does have a lot of this chemical perchlorate in it. And you've probably maybe even seen some recent news reports about how perchlorate was considered a bad thing for current life on Mars, and maybe even worse when it's irradiated by UV light. So when you have soil, the problem is it gets a lot of that perchlorate, and it has a lot of surface area, so it gets a lot of ultraviolet light. May not be the best, but you know, if you could drill a lot of holes in that nice gray rock that has the more, you know, less altered stuff, and maybe make some soil out of that. I'm not an expert in this, but that's just my 2 cents. And your second question, what was the second question again?
Making glass.
Oh yeah, I suspect that's possible like it is on Earth, because a lot of the rocks are made out of very similar chemicals and minerals as on Earth, including silica.
Thank you.
First of all, thank you guys so much for what you do. This is such an amazing thing that everybody does here. Yes, ma'am. Thank you. Thank you guys for what you do here. It's such an amazing thing. I have 2 questions. Elon Musk just released a paper about his general idea about how to get to Mars. So I wanted to see if you guys, number one, do you work directly at all with him, or just share data and what you thought about that? And then the second question was about how you send commands to the rover, because I know it's not an instantaneous process, and do you stack up a whole series of commands that they have to be in certain orders, things have to move before another thing? If commands get there late, could it mess up? I'm sure that's stuff. So thank you guys again for all that, and I'll take my question away. Thanks.
You want to tackle Elon?
You take the first one.
Okay, there's several ways that JPL is involved with Elon Musk's organization, among other things for helping him to understand the kinds of navigation that we do to get to Mars, and providing information for him on how he's going to have to do some of that as well. And clearly, if he's able to do what he would like to do, which is to start sending spacecraft and landing them on Mars in the next few years, actually, we might end up being a customer for providing some payloads that he could transport. We're always interested in options. So that's some of the things that we're thinking about with that. Anything else?
No, I can talk about operations real quick. Everything you said is basically yes. So we send up a series of commands every day. Mars has about 7 to 22 minutes, I think, is the range of waiting time for signals at the speed of light to get to Mars. And so if you were to say, turn the rover right, 15 minutes later, the rover gets that, it turns right, and then 15 minutes later, you get the response that I turned right. Horrible way to operate a rover on Mars. And so we actually send up 1 full day's worth of commands every single day. Well, actually now 5 days a week and 3-day set of commands on the weekend. And the rover is built to execute all those commands on its own and knows how to check a lot of things for its own safety to make sure that the humans hadn't told it to do anything stupid. We also do a lot of checking of everything on Earth before we ever send it, of course. Everything you said about, we could, there's this, there is a gap where, we send up full days worth of commands when the sun is rising on Mars. When the sun is setting on Mars, the rover sends back its data, and we use that data to plan the next day. But something could have happened overnight, and our new commands get up there, and now the rover is in something's gone wrong when it receives our commands that were built on assuming everything was fine. But it's also smart enough to know how to handle that, and then it would tell us it's in trouble, at its next opportunity. Of course, the most challenging part is that Mars has a 24.5-hour day, so we can never quite stay in sync with the Mars sunrise and sunset. We actually get out of phase with Mars every 3 weeks or so, and then back in phase 3 weeks later.
Hi, regarding the alpha particle X-ray function on the spectrometer on Curiosity, has it located any additional information in regard to perhaps locating a new mineral?
That's one of our real useful instruments. So we sort of have a pattern that we use where we first drive and take pictures. And if something in the pictures is really interesting, we'll approach it with the rover, get out the arm, and then place this alpha particle X-ray spectrometer, which emits alpha particles and X-rays, and then reads the X-rays emitted by the rock. And that's actually a nice technique to figure out what the rock is made out of. And if that is looking good, then only we would spend the effort on drilling it. And so most of the rocks on Mars are very similar to rocks you'd find on Earth. Mars and Earth formed a similar part of the solar system. They're sister planets in that sense. But we have found, not with the APXS, but with our X-ray diffractometer, which actually shines X-rays through rock powder and makes a little rainbow pattern, like a diffraction pattern, like light through a prism. And we found a mineral on Mars that no one expected to be there called tridymite, which is a crystalline form of silica in rocks, and is quite rare on Earth, and it indicates that on Mars there was a lot more evolution of the magmas under the surface than we ever expected. It's kind of a mineral that only forms when there's been circulating magma interacting with water and things for quite a long time, instead of the more pristine basaltic minerals that most of Mars is made out of.
Thank you. Good lecture.
Thank you.
I was wondering, with the 2020 rover, what's the plan for sample return? You mentioned if we can get them back or something like that.
Okay, sample return is a lecture in its own, but put it the following way. It looks like right now that with the technology we have, it's going to be a 3-part journey. We're going to have to break it into 3 different missions, so to speak. The first of which is to find the right things on the planet, take samples, and get them ready to be brought back. Once we've done that, we have a vehicle that collects them, puts them inside a little rocket or some other similar technique, and gets it up into Mars orbit. And then the third leg is to go to Mars orbit, capture them safely, both in terms of protecting the samples, but also making sure that the vehicle that is going to bring it back isn't contaminated by the samples, and the exterior of that vehicle or return capsule or anything else isn't contaminated by the surface of Mars, so to speak, and then bring that back to Earth. And then we have the ability to study these samples not only with the latest scientific instruments at the time, but keep them in storage for new and better techniques that might be developed in the future.
So is that three-mission thing you described part of the 2020 plan, or is that something that comes later when available, when
Right now,
funds are available?
2020's, one of their goals is to prove out the encapsulation, the sample handling, storage, and deposition for the future. Now, whether those particular samples that were cored and contained with 2020 are going to be the ones that return, or whether this precursor mission is really a precursor and there will be more and better ones that are in the future to get other samples in other areas, we don't know. But right now, 2020's job is to prove that this can be done.
Hello. Do you see any potential applications of swarm robotics to Mars exploration? And if so, what would be the key benefits and the key challenges?
Swarm robotics. Do you know anything about that?
I'm afraid the concept of swarm robotics is kind of too far out there for us to really plan a mission on it. We usually tend to make use of very well-defined, well-understood technologies. It takes a lot of proof to make sure that we can do something to get that into the latest mission. So it might be a while.
Thank you.
In a similar vein, though, I was just going to say, so to end that on a slightly positive note, there is we will be, we're thinking at least about trying to fly a helicopter with the Mars 2020 mission, which would have the advantage of scouting out ahead of the rover and looking for potential places that the rover might traverse, getting some advanced imagery, advanced chemical information perhaps, and then, of course, as Jim was saying, just learning how to do that. We started, Curiosity is the third generation rover on Mars, and we went from the shoebox-sized rover to the golf cart to the car-sized rover in 3 generations. But we got to start somewhere, and the helicopter, a single helicopter, learning how to fly that on Mars is the start of what could end up being a nice swarm of vehicles later.
Okay, we'll take 2 more questions from the microphone and then move to the other centers.
Well, I have a real estate question. I don't know if it's fitting to ask 2 scientists, but who owns Mars? Are we going to fight over this? Number 1. And number 2, so it's obvious there was water before, but it's gone now. So are we hoping that we can transplant water or make water appear or make water because we want to live there? Is that that's not possible. We can't make water in a dry planet, is there?
So start with who owns Mars. I can't give you the legal definition. There probably is one. But a good analogy to think about with Mars and even the Moon and other planets is Antarctica. So no country owns Antarctica, but we agree among nations to treat it in a certain way and to do science there and not interfere with each other that are doing science there and not plant a flag there and claim it for yourself. And so that's the sort of working model that we would have for planets as well. Until, long time from now when people are actually putting civilizations there, as it's a scientific target, we would treat it like we currently treat Antarctica.
So are we the only country who sent a robot over there?
No, right now we're the only country that successfully landed, but there are orbiters. There have been orbiters from from Europe, from Russia, from India, and I think China has one on the way, and the UAE has one on the way. So it's quite a few nations. I'm probably forgetting some. And then in terms of water, there is a lot of ice on Mars. It's up near the poles, so more water than you could ever make use of. I think if you spread it around Mars, it would be 30 feet deep of water covering the entire planet. That's how much water is trapped in the poles. So you could make plenty of water up there. But if you want to near the equator, Mars also has a tiny bit of water in the atmosphere, and you could just slowly get that out of the atmosphere. There's also water in rocks, like clay minerals actually have water in their atomic structure, and so you could find a way to extract that water as well. So all these things would be looked at for astronauts.
And one more, which is there are some ancient buried glaciers that are up at the mid-latitudes.
True.
Not at the equator, not at the poles, but kind of in between. And they might be a very useful source of water that's a little more manageable to get to than way up at the North and South Poles.
So you're saying it's possible? But there might,
Yeah.
we might be able to live there with water.
Yes.
Thank you. I think she wants to go.
So, if it was like very likely that there was some sort of life on Mars, like what type of life would it be like? Would it be like single-celled organisms or more advanced animals or plants like fish?
It depends how long life had a chance to evolve and what Mars offered in terms of niches for it to evolve into. At this point, having mapped the planet very rigorously from orbit and having seen a lot, not a lot, having seen a tiny amount of the planet in great detail from I think 7 landers now, the idea that we're going to one day come across plants or footprints of dinosaurs or something probably is faded away at this point. But the microbes are by far the dominant life form on Earth. We mean nothing in terms of the biomass of Earth, and so there's a great potential for life to have evolved and been vigorous on Mars as microbes for a long time, as it was on Earth for the first few billion years of life on Earth.
Okay, let's go to the other centers.
Okay, these are from the web.
Oh, from the web. Okay.
Diego, hi Diego, asked, what are the top theories of where the water went? So the top theories of where the water went all have to do with the way Mars, it's sort of a Cinderella issue. Is that the right analogy? No. 3 bears. 3 bears, thank you. Goldilocks. She knows. Goldilocks. Wrong fictional character. Yeah, a Little Mermaid. No, so it's the not too hot, too cold, all that. But in the case of Mars and Earth, it's the size of Mars. So Mars, as you saw in that initial picture, is about 1/3 the size of Earth. It has more. That means it has more surface area compared to its internal volume, and planets that have more surface area give off relatively more heat, and they cool faster. So earlier in Mars history, its crust thickened and cooled, and that probably led to its magnetic field turning off earlier than Earth's did. Earth hasn't turned off yet, actually. So once you cool the crust and turn off the magnetic field, you leave the atmosphere vulnerable to the solar wind stripping it away over time. And also because Mars is just physically smaller, its gravity is less strong, and the atmosphere can actually just be lost due to being lost to space because the gravity is not strong enough. So there's a few theories like that would all lead us to believe that Mars' atmosphere over time has gone away. And in fact, there's a mission called MAVEN, which is an orbiter at Mars right now, that's actually been showing that even today, Mars' atmosphere is being lost by the solar wind through this process. And you can calculate how fast it's being lost today and figure out that over time, this theory actually holds up quite well.
Okay, the next one is from the coffee enthusiast. And he asks, is it possible that Mount Sharp was caused by volcanic activity, or has it been entirely from sedimentary deposits?
Good question. So we haven't found any evidence of volcanism. The tridymite, actually, I mentioned earlier, can be found around volcanoes on Earth. But So far, there's no vents, like no lava flows, no fissures where magma would come out of that we found anywhere near there. And plus, the layers themselves are very flat on Mars, whereas a volcano, if you all made one in your science fair project, they come out and you get layers that sort of conform to the shape of the mound instead of being flat like you've sliced a cake. And so the Gale, at least the bottom part of Mount Sharp, where we are, is the cake model. And the upper part is not the volcano model, but it's also not layered. It's just massive. It's just thick. And so we think that could just be wind-blown dust that came in and just made a big, thick layer.
This is the interesting question. Jeff asks, what has surprised you most during this mission? And I'll take a crack at it first. I always like to be interested in the science that happens, but it's more fair to leave that for Ashwin. The things that have surprised me are things that have happened on the vehicle and how well we've been able to respond to the challenges that we've gotten with the flight team, basically solving everything we've been thrown at yet. Now we've got one problem we're currently working, which has to do with the drill not working quite right. And we're, I think, well on the way to solving that to the point where we're going to be able to drill again fairly soon, where fairly is in months, not years and not weeks. And it is one thing that JPL does well, and it's one thing that JPL's people does well, is deal with the problem that they have and get the most science from a vehicle, run it into the ground, get everything you can from it, so you don't end up leaving a perfectly good rover on the surface because you were trying to baby it too much. You wear it out.
Yeah, I should probably have prepared answers for these kinds of questions. I don't know if there's any one thing that surprised me, but one thing that certainly comes to mind is just how abundant the evidence for lakes and water has been. Like we were really nervous about going to Gale Crater because we haven't been to Mars a whole lot, and it could have been a strikeout. You know, like we convinced those of us who were championing Gale Crater as a landing site had to convince a lot of other scientists that it was the right place to go, largely because it contained the record, you know? And so the argument that won the day is it's going to tell you a lot of Mars history. The problem is a lot of Mars history could have all been boring and blown in by wind and, you know, no water involved. We had good reason, of course, to think that water was there. But, you know, from the day we found the rounded pebbles till today, it's just been water, water, water. And that's been really wonderful to learn about ancient Mars that way. I think our last online question, Finding Freedom, asks, how are the images processed to make the sky appear blue on Mars? Yeah, I mentioned that a little bit earlier, but we cheat a little bit. The sky is kind of salmon colored. There's all this dust in the air and it's sort of orangey dust, the color of Mars dust. And it tints everything orange. And so when you just snap a picture with our cameras, you get an orange sky and a very orange set of rocks. And we process the colors. We basically use like something similar to a white balance function on Photoshop, where we can retint the colors and remove the orange cast and make it appear more like it would look if those same rocks were on Earth. And we do that to allow our geologists to use their sort of, you know, subconscious skill set. You know, we have geologists on our team who've spent their life walking around very similar rocks in the deserts on Earth, and they recognize it helps their intuition when they see rocks and minerals in the colors that they see them on Earth. So that's sort of why we do that. Final question? No? Okay, we got one.
And go to the microphone, please.
Hi, Ash. Hi. When you were mentioning about tridymite, have you considered the fact that when silica is amorphous, and it's deposited amorphous like it is from fluids, that it can also devitrify into cristobalite and tridymite, like in petrified wood or in snowflake obsidian, for example, that you don't actually need the high temperatures to get the tridymite, which would be more compatible with the low temperature formation of your phyllosilicates?
Thank you very much. I'm not the expert on the tridymite discovery, but I will bring that back to the team. a real life geologist. Sure. Okay, well, we want to thank you on behalf of the, actually, since it's the 5-year anniversary, in the literally, thousands, 3,000, 4,000, 5,000 people who helped develop MSL, the Mars Science Laboratory, and Curiosity since 2003 or so, and the 500 scientists around the world in like 7 or 8 different countries who operate it today, and the about 200 people at JPL who keep the rover going every day. We want to thank you all for coming and keep watching.